All right. Go ahead and read it to us.
A pendulum swings from point A to point B as shown. Without accounting for friction, how fast would the pendulum bob swing through point B? If the pendulum loses 5% of its energy to heat from A to B, how fast would it swing through point B? If the pendulum loses another 5% of its energy swinging back to A, how would it swing? So
let's just focus on the first part. You let it go from here, it's going to swing down to the bottom. How fast is it moving when it swings through the bottom? If there's no friction.
So we did our, original bar graphs with no friction. So we had EG equals mgh. So it would be the mass of the block, is 0.2. And then the G field would be 10 as usual. And then our height is 0.8. So when you do the calculation, you get that it equals 1.6 joules. So then we knew that it would have to be the same for kinetic energy because we didn't lose any to friction. So we set 1.6 equal to 1/2, and then times the mass, which is 0.2, gives you v squared. So v squared equals 16, and then you would have v equals 4 meters per second.
So here's what I like about this, right? Is you look at their blocks, you look at their bar charts, you get all gravitational to start, 1.6 tall, and there's no friction in the system at all or in the situation, then whatever you started with gravitational, you're going to end with all kinetic, 1.6. And then since you know the kinetic energy value, you can just solve for the speed directly. You guys with me on that? That's why I like this problem, because it gives you a sense of it's called the concert. Can you get off my table, please? I don't come to your house and put my butt on your tables. Get off there. It's called the law of conservation of energy, the fact that we have to keep track of all the energy at all times. That looks pretty good. So what does it say? It says, now, what if you lose 5% of your energy?
So when we lose 5% of our energy, we'd have to take our amount that we have of energy now, so that would be 1.6 joules, and then multiply it by 0.05, because that would obviously represent the percentage of energy we're losing. So then you get 0.08, and then we subtracted that from 1.6 joules. So then the kinetic energy left would be 1.55 joules.
I think you mean 1.52 joules. Because 1.6 minus 0.08 would be 1.52.
But yeah, so then we did it again in...
So I think it's just a typo here. You guys see what I'm saying?
Yeah, I do.
So this right here says this is how much energy you lose. And so if you started with 1.6 and you lost this much, it would be not 1.55 but 1.52.
So if we 1.52 times 1.5.
It's fine. It's fine. What I like about this, though, is if you have a new kinetic energy value, you would have a new speed. Okay? That's fine. It looks really good. Are you guys okay with that one?
Yeah.
All right. Let's move to the next one. What do we got?
So,
Hold on.
oh,
Let people get situated. We'll go. All right, go ahead. What's the problem setting? So this one's interesting because it's a little bit different. All right. So go ahead and read it out loud.
okay. A balloon of mass 25 grams 0.025 kilograms, strikes a block of wood and comes to rest. The wood exerts an average constant force of 50,000 newtons on the bullet, opposing its motion and bringing it to a stop. How much energy is lost to heat? So for the first part, oh wait, no. How far into the wood does the bullet penetrate? So we calculated the kinetic energy of the bullet originally and before it hits the block. So it'll be 1/2 times 0.25 times 90,000 because 300 squared is 90,000. And that would be 1,125 joules. And then,
All right, hold on. So what's the speed?
300 meters per
300
second.
meters per second.
300 meters per second. So we did 1/2 the mass, which is 0.025 times 300 squared.
Mhm.
Okay, and you got 1,125 joules.
Yeah.
Okay, so, well, it says 10,000 on your board. You want it to be 90,000?
Oh yeah, it's 90,000.
That's why I was a little confused. There we go. Okay, so the first part says, what's the kinetic energy of the bullet, right? Now, the bullet hits the block and sticks in the block, right? Where did all the energy go?
Thermal.
So once it's stuck in the block, there's no more kinetic energy, there's no elastic energy, there's no springs or rubber bands or anything. It has the same height as it did before, so it didn't gain or lose any gravitational energy. Energy has to go somewhere. And when a bullet hits something, it totally heats up. In fact, I should have queued one up, maybe we'll look for one at the end here, but there's videos of bullets hitting, let's say, a hard piece of steel, and it hits and heats up so much that it melts the bullet on impact because there's so much thermal energy generated. Kind of a cool thing. So what they're going to do now is they're going to say, well, how much thermal energy was there? How much thermal energy was generated then?
1,125 joules.
Totally, because all that kinetic energy had to go into thermal energy. Now, the next part says, how far did it penetrate? In order to know this, you have to know one thing that we haven't talked about as a group because I skipped it. And that is that if you want to figure out how much thermal energy is generated, you take the force times the distance. Okay? All you got to do is take the force times the distance. All right? So what's your force?
So our force is 50,000 newtons.
Mm-hmm.
And then the thermal, you would have to plug the kinetic in, so it would be 1,125 divided by 50,000, which gives us 0.0225, and that would be the distance in meters.
So you look at the line that says E thermal is equal to 50,000 times D. That line is important because it's the force times the distance. Okay? We're going to see that force times distance relationship again here in a second, but keep that in mind that it's force times distance. Okay? Got it? If you want to figure out how much thermal energy is generated, you take the force times the distance. Okay? Let's do one more.
Did you want me to start?
Just give people a minute to get
Oh.
situated.
The question?
Oh, it's number 5.
Okay.
You're welcome.
All right. Go left.
A 0.4 kg block is propelled along a rough surface by a compressed spring and slides to a stop. What is the force of friction between a block and a table? What is the coefficient of friction between a block and a table?
So we're not going to try to find the coefficient of friction,
Oh, okay.
but we just want to know if we can figure out the frictional force. Okay? We just want to know if we can figure out the frictional force. So tell us that, give us the energy bar chart situation.
First we found the elastic, which is 2 joules, and then we like to realize that it's exactly the same as the thermal energy, and then we just like plugged it in, the like equation, and then we found the force.
So what's the energy situation in the beginning?
What?
Where's the energy in the beginning?
The elastic.
It's all elastic, right?
Yeah.
And did you calculate that?
Yeah.
And how much was it?
2 joules.
2 joules. That sounds really good. But when we look at the block later, it's not moving. So there's no kinetic.
Yeah.
It didn't go up any hills, so there's no gravitational. It's not pushing or pulling on the spring anymore, so there's no elastic. So if you notice, there are no bars in their second graph. Right? Where'd all that energy go?
Thermal?
It was released as thermal energy. So, if you want to find the thermal energy, you need to take the force times the distance. In this case, it's the frictional force. So how much thermal energy are we talking about here?
2
2
joules.
joules.
2 joules. And then what's the slide distance?
0.8.
0.8 meters. And you calculated how much frictional force?
2.5 newtons.
2.5 newtons. Yeah, that looks good. Is that cool? All right, we got a couple more. I think we can probably get to those tomorrow. If you presented, erase your board. If not, do me a favor, put your board back over on the side.